I'm going to suggest that we skip around the paper a little bit and make the most of our time here with Bea. So I'm going to suggest that we start with the plain language summary, which is a kind of simpler version or a plain language version of the abstract. And then maybe we should do the key points. And then maybe dive into the figures. And then we can kind of tackle the conclusions later. But just this is meant to give a good introduction to this paper so that when Carlos takes us through this paper and we have another meeting about it, we can really start to hash through it as well. So why don't we get started with that? Would anybody like to read the plain language summary?
I can, if no one else.
Oh, great. Thank you, Alexa.
Sure. Okay. So a variety of optical structures are observed in the subauroral region. This region is at lower latitudes adjacent to the auroral zone. These phenomena are distinct from auroras as their optical signatures appear to be triggered by extreme thermal and kinetic energy in Earth's atmosphere, rather than produced by energetic particles raining down into our atmosphere. Two such subauroral optical structures are stable auroral red arcs, or SAR, and strong thermal emission velocity enhancement, STEVE. Although SAR arcs and STEVE both occur during geomagnetically active conditions in the subauroral region, their appearance differs significantly with distinct spectra, scale size, and duration. We combined images captured by a citizen scientist in New Zealand on the 17th of March, 2015, with data from a scientific all-sky imager as well as satellites. We observe the evolution of an unusually bright SAR arc into STEVE. We show satellite measurements of a region of fast-moving particles known as subauroral ion drift at the same time the SAR arc occurred. Later, when STEVE was present, these conditions further intensified into a narrower band with higher temperature and faster flows. These observations highlight the benefits of combining citizen scientists' observations with scientific data to help discover new connections in geospace.
Excellent. Do you have any questions about that? Or summary of what the paper is going to be entail here?
So it basically seems to be discussing the characterization of time evolution of Aurora, where they're looking at two different definitive structures, the SAR arcs and STEVE, and the two different types of kind of auroral structures were observed by using both citizen scientist data and a more like, I guess, official scientific apparatus, and yeah, used in conjunction to get a fuller picture of the evolution.
Yeah, definitely. The conjunction of the data are really key to this result, and then the time evolution. So I think that's what the figures are going to show, especially if we just kind of look at those and then along with the text to highlight that.
I have a question.
Yeah.
So it sounds to me, and pardon me for taking this to super simplistic, but it sounds to me like what they did was looked at SAR arcs and STEVEs from above with the satellite and below from the ground, and they saw the SARs turning into a STEVE. Does that imply that they're like very like different evolutions of the same thing? Like, is a SAR arc a juvenile STEVE?
I think that's what we're trying to figure out. We can skip to the conclusions with your
if I can interrupt
with your question, or we can allow Bea to answer.
Yes,
it,
please.
Which would be great too.
So there were several things, and that's what we were trying to capture in the plain language summary. So below the auroral oval in the subauroral region, we have typically, and what I say typically for the last 30 years, people have been analyzing these red arcs, the SAR arcs. Carlos actually has done a fantastic work understanding the physics that produce the stable auroral red arcs. But then in the same region, we observe those multispectral arcs that we know as Steve right now. And one question that, since the very first interaction that I had with Carlos, that is passionate about SAR arcs, and I was deeply into Steve, was, well, these occur in the same region. They're both optical phenomena. Is there a relationship between these two arcs? And that's what we were trying to see. So this event is telling us that one of them can evolve from the other. And there is a new paper coming up by Megan Gillis where she's analyzing the relationship even further. So this is the very first evidence that yes, SAR arc could be kind of observed at the beginning of Steve, and then Steve occurs when the conditions in the ionosphere intensify even further. And that's what the paper is doing.
Yeah.
Cool.
So,
thank you. Yes.
I'm not sure that means the SAR arc is a baby Steve or vice versa, but we'll kind of keep thinking about that.
And again, this is one event. So one event means one case. We don't know for all of them.
Yes. And so I was also going to point out a couple of things about the paper I forgot to earlier, but this is a paper in Geophysical Research Letters, which means that it's nice and short and also a nice new result. There's kind of standards for what would be qualify for Geophysical Research Letters. And then at the top left of the article, there's key points, which also kind of goes over what we've talked about already, that this is the first time the evolution of a SAR arc into a Steve has been shown, and that this is using citizen scientist images. In this case, Ian Griffin from New Zealand is one of the citizen scientists. Is there another one on this paper, or is he the only one?
He's the only one.
Okay, great. And then a little bit more in the key points. The second key point, I'll just go ahead and read that. An all-sky imager measured a bright 6 kilorayleigh SAR arc co-located with the arc observed by the citizen scientists when the emission height is 425 kilometers. And then the last key point is that swarm data show subauroral ion drift conditions during a conjunction with the SAR arc observation. And later, these conditions intensify when the Steve is measured. So let's go into the figures and kind of walk through the figures if we can. And Bea, do you have any other anything else you might like to add?
I can add several things about SAR arcs and why in the key points we wrote that is 6 kilorayleigh and why that's important. And that's because SAR arcs are usually very dim. They're subvisual, they're hard to capture. And on this day, Ian, when he took these images, he was driving back because it was late at night, and then he was driving back home and saw this beautiful bright red arc in the sky, very unusual. Parked his car. I think he got a speeding ticket in between parking his car and seeing the SAR arc, and started taking videos of it. When we analyze the luminosity for the SAR arc is at least an order of magnitude 10 times brighter than what Carlos usually observed with his data. So this is, as I was saying before, one event, but one event that is showing us that this SAR arc is extremely bright too. So it's a very particular SAR arc.
Okay, great. Let's see. So Laura, are you able to show, maybe it's just my screen, the figure and the caption here? Does anyone want to read the caption? And then we will probably we'll kind of point to what the caption is describing.
Unfortunately, I can't zoom out any further, but yeah.
I think it's my, okay. Does anybody want to read the caption?
I can do it.
Okay.
Figure 1, A. A wide, stable auroral red star arc is observed at 9:27. UT is
Universal time.
universal time. Thank you. A strong thermal emission velocity enhancement, Steve, at 9:51 center, and a partial arc with green picket fence structures at 10:02 universal time, right. Auroral activity is observed at the bottom south of each image. West is to the right, B, C, and D show decomposed images in red, green, and blue colors, respectively, at the same times as panel A. At 9:27 left, no arc is observed in the green and blue channels. At 9:51 center, the 3 channels detect the arc. At 10:02 right, the main emission comes from the green channel, where picket fence structures are observed. A partial arc is also observed in the red channel to the right of the image. Here is best I can do to get all of them up there.
Do you want me to walk you through this?
That'd be lovely.
What questions, do you have questions from reading that, Laura?
I have many questions from reading that.
See where to start in terms of the orientation. So the columns are the 3 times, and then they're broken down into the red, the green, and the blue, and all the colors, I think, at the top. But what do you have other questions?
So I guess my questions are, so I think I'm having a little trouble understanding what the red, green, and blue are, because I think with my non-science brain, I would expect that if I was looking at something in reds, then the things that were red in the picture would kind of blend into the background, and the things that were not red would stand out. But it looks like it's the other way around. It looks like the things that are the same color as the colors are standing out. So I think I'm having a little trouble understanding what the colors mean.
So the photographers understand this better than me. So if I'm misexplaining it, please interrupt me. The first row where we have the color image is, that image is composed of channels, and the channels are red, green, and blue. So when we analyze the image, we can separate into those 3 channels that you have in B, C, and D. The red channel is sensitive to everything that is red. So the red colors are going to pop up. And it's the same for the green and the blue. If we were to take these 3 images, B, C, and D, and combine them together, we're going to get A. So that's exactly what we did. When we look at the first column, that's the time of the SAR arc, at 9:27, we looked into the channel, and you can see that the red is extremely bright. We see absolutely nothing in green and nothing in blue. So that is telling us that most of that emission is happening in the red channel, and that is consistent what we know about the SAR arcs. The SAR arcs are usually termed as pure red emission. And in this case, we are seeing that most of that emission is occurring in the red channel. When we look at the time for Steve in the central column at 9:57, and we separate into the channels, you see that there is emission in the red channel, in the green channel, and in the blue channel. And that is also consistent to some previous studies that show us that Steve is actually different because it's in a continuous spectrum. So all the wavelengths, all the colors are being excited at that time. And that's why we are seeing a continuous emission in all of these 3 channels. And then later on, we're observing the picket fence. And I highly recommend you, if you don't have access to the movie, we have in the supplemental material the movie of this event. But in the last column, we have the picket fence. And when we look at the channels for the picket fence, we see maybe a little bit of red on the right edge. Yeah, so that's probably a remaining of the SAR arc Carlos was discussing. We clearly see the picket fence in the red channel, and we don't see much in the blue channel. So that is telling us that the picket fence is, as we have observed in other instruments, purely green spectrum. So that's kind of the summary that we wanted to make with these images.
And then, is it true that these are Ian's images, and this is like kind of an all sky, but the way it's described in the text is it's a fisheye lens pointing towards the south. So it's not the same as a typical all sky image.
No. So what we did for this paper, there is a camera, an all sky camera from BU further a bit north of where Ian was located. And we used that to kind of calculate the luminosity. Unfortunately for that all sky camera, the sky conditions were a little bit cloudy, so they're not the most stunning pictures. So we base most of the study on Ian's images.
Yeah, so figure 2 shows those images from Mount John Observatory, right?
I think Michael has a question about figure 1 first.
Oh, great. Go ahead.
Yes, just a short, simple question. How do you convert the raw image into these color channels? So there are different ways to do that. So one way is to extract the raw counts from the camera and put them into the channels, or you can convert the image, let's say, to a TIFF file and then extract the color channels. The results could be different. So the question is, how does it work in this case? Do you use the raw counts or?
I used the raw. So what I did is I loaded, like the very technical way I did it, I loaded the full image, the raw image into IDL, and IDL reads that as the different raw channels. And I have color coded the different channels.
Yeah, okay. Thank you.
Yeah, no problem.
Okay. Should we go into figure 2 a little bit? Does somebody want to read figure 2's caption?
I can do caption.
Okay.
Figure 2, top. Unwarped all-sky images from Mount John at 9:25 and 9:38 Universal Time, using a height of 425 kilometers and zenith angles down to 80 degrees. Near zenith and to the east, no clouds were present, and the brightness of the stable auroral red arc at about 45 degrees latitude was about 6 kilorayleigh. Bottom. Unwarped image from, I'm sorry, the only way I know how to pronounce this is how they do it in Florida, so apologies to folks down south. Dunedin at 9:33 Universal Time, using the same parameters as in Mount John. Blue lines represent geomagnetic latitudes. The western edge of the arc is wider and brighter than the eastern edge.
Which side is west here? Okay, so that must be the left, the western side of the arc. So, Laura, what questions do you have about this?
I'm trying to, so this is north of where the south-facing fisheye lens was. So the stuff that Ian was seeing would be towards the bottom-ish, but it looks like it's a little higher. I think I'm just trying to think in my head of about where just positioning myself and thinking about where these two cameras are spatially. Also, why is there a is that New Zealand? Why is there a New Zealand in the middle of the all sky?
So that is unwrapped. Like the very first word that Carlos used, and we use different terminology. So Carlos is going to say unwrapped, and I'm going to say mapped. So what we do is we take the images that we're capturing from the ground, and we are rotating them, and now we're looking like we are looking from above.
Oh, cool.
So right now you're looking at the arc mapped, so plotted into the map, like we're looking from above. And that's the easiest way to observe for us. Many times it's the easiest way. So what you have here, the two upper panels are the camera from the BU, and this is at Mount John. And Mount John is slightly north of where Ian was located. So the lower image is the mapped or the unwrapped version of Ian's image. And if you can see, this covers slightly southward than the image above, showing that these two are spatially separated.
Okay, thank you. I think that helps with my figuring out the spatial imagining myself too.
Yeah, okay, so the color one is Ian's image from Dunedin. Do you know how to say that?
I have heard Ian saying Dunedin, like similar to what similar to what Laura said. Yeah,
I love it. In Florida, they call it Dunedin. Dunedin. So.
He said something like that. Carlos and I butcher the word. I cannot tell you.
And then, and then this unwarped image in the bottom is at one of the times, 9 or so not exactly at the same time, but is it kind of, why did you pick that time? You picked that time to line it up with the Mount John, or?
Because at that time we had better Mount John imagers. So Carlos was calculating the luminosity, and since the cameras at Mount John are calibrated, we can calculate the physical units of the luminosity, and that's how he obtained the 6 kilorayleigh. Unfortunately, as I said, the camera gets extremely cloudy afterwards. So the only time that the data at Mount John is good is for part of the observation of the SAR arc. So that's why Carlos used the images to give an idea of how bright the SAR arc was at the time of the observation.
And just to follow up on that really quickly, a kilorayleigh is a degree of brightness?
Rayleigh is the unit of brightness. So a kilorayleigh is 1,000 rayleighs.
Okay, thank you.
Which is about a visible auroral arc, about 1 kilorayleigh, if I recall correctly. So 6 is a pretty bright auroral arc.
But it's red, so you need a little bit more luminosity.
And this Mount John Observatory is only looking at 630 nanometers in the red. So then your equivalent, your kind of calibrating Ian's camera's red to the Mount John brightness, which is only in red. Is that a fair way to say it?
Yeah. Okay. This particular camera is red. So you're seeing at the bottom that says Mount John, 450 kilometers, 80 degrees field of view, 630 nanometer. That gives us the information of the wavelength that is measuring. So that's red. But I'm not sure, and that's a good question for Carlos, if in Mount John they have other wavelengths, because usually the BU sites have multi-wavelength instruments. So that's a good Carlos question. Mm-hmm. But this one in particular is only red, yes.
Okay, great. So if you have to go, we understand. You're welcome to come back for the next meeting if you are able to. And appreciate your help with the paper. And we will, you have this link. We might put more questions or get back in touch with other questions as well. So,
and feel free to email me questions. I'll be happy to answer, and the same for Carlos. So yeah, anytime. Very nice to meet you all. I'm sorry I have to leave.
Oh, well, we're so glad to have you here. Thank you so much for joining us today, Bea. We really appreciate it.
Bye, everyone. Join the Steve workshop next week.
So excited.
Bye.
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 Awesome. Thank you. All right. Well, we are doing good on the paper here because now we have sort of the orientation of the data. to start to get into the conjunction with the satellite data and what that was seeing and how they are drawing conclusions from how that looks. So I think I think we can keep going because figure 3 and 4 are sort of the key points here, as far as you have this unwarped image from the citizen scientist, which really means mapped. So they took the citizen scientist image and then mapped it into what it would look like if you were looking from above. And then there's a satellite that makes a pass through this as well. Okay. Anybody feeling like reading figure 3?
I can do it.
Okay.
So on the left, there's an unwarped all-sky image from Dunedin, assuming an emission height of 425 kilometers. Swarm B trajectory is indicated as a blue line. On the right, plasma parameters measure along the pass from top to bottom: electron density, N sub E, electron temperature, capital T sub E, and horizontal plasma drift velocity. And electron density shows a small decrease coinciding with the stable auroral red arc location, which is the horizontal red line. A collocated electron temperature enhancement is observed, and the horizontal plasma drift velocity shows a peak of about 5.5 kilometers per second. This peak seems to be a thin extension from a wider structure, peaking at around 3 kilometers per second. Symbols indicate peaks in the plasma parameters. Symbols indicating peaks in the plasma parameters were added in the plots and in the image to investigate their location on the arc.
Okay. How do you feel about this, Alexa? Jumping into the deep end of the pool here, as far as, I don't know if you've looked at some of the other Steve papers, but yes.
This feels a little more foreign, and I'm kind of, right now, I'm absorbing the information to the visual aspect.
Yeah, so I was kind of, the swarm data, the swarm B, there's multiple swarm satellites. So the trajectory of the swarm data is shown in this map on the left, the image, as the blue line. And the plasma parameters are measured all along the pass, which is the time is on the x-axis of the plot. And the plot on the right shows the swarm data. These were used in the original Steve paper and a few other Steve papers that have conjunctions. So the density is one of the measured parameters, the electron temperature, and the horizontal ion speed in the cross-track direction, which means perpendicular to the trajectory of the satellite. And I think the kind of red points are sort of picking out where this is crossing the arc. And there's some assumptions going into this with the height, because the mapping height kind of moves where you where that crossing point is, and then you know, how wide the arc is being crossed. How wide the arc is apparently, I think, is the kind of width of this horizontal line on the right-hand side of the figure. And they may talk about that assumption of height elsewhere in the paper a little bit more. Let's see. I was trying to make that note to myself to possibly look at that. But one thing to see here. So what you see at when it crosses the red, which the red at this time of 9:40, I think we're interpreting this time also notably is kind of between the SAR and the Steve. We might need to look at that whole video to see how that evolution is happening. But if we go with the red being the SAR arc here at this time, what we see is, you know, some notable peaks in the electron temperature and notable velocities in the cross-track direction of more than or about 6,000 kilometers per second. Sorry, 6 kilometers per second. These are similar to what's seen usually crossing Steves in the past. And then, especially in comparison to the time of the next figure, we're kind of going to see how it changes. So I wanted to try to give a little bit of orientation to that, but let's talk about questions with this. Laura, were you going to say something?
Oh, I was just going to confirm my understanding that this is happening at the same time as this, and this, the satellite. I don't
know what you mean by this.
Sorry. I'm wiggling my mouse.
I'm not looking at your mouse because I'm trying to read
the photo
okay.
And the chart, the photo being the ground-based, the chart being the satellite, are happening at the same time. And the little place where there's like a little star on the photo is the same place that there's a major blip on the chart on the right. And what it's saying is that's a weird thing that's unusual and they're looking closer at that.
Yeah, the photo is only at the same time so time is marching along on the satellite track. So you just have a photo at one time.
Okay.
Yeah.
But roughly while the satellite is marching along, the SAR/Steve is staying more or less in the same place. Is that what this is kind of showing?
What the photo is at the time, that's the, you know, peak conjunction time there, okay. Basically.
Cool.
So there is a whole video of how it marches along and how it moves, and it would be probably the video in the appendix is not, it may or may not be mapped like this. But you can kind of see how it moves, and compared to the next figure, we can also see if that arc is moving north-south or the relative motion in the sky. That's a good question, because that's part of the evolution of these structures also.
Okay, thank you.
We're kind of skipping rapidly through the paper here, so that we can, you know, there's much more to read in it, but just to get the overall overview here. So let's continue on, see what the next figure reveals. And this is sort of a way to, it's a way to read the paper. Obviously, you do want to read the words about the description of this. But it's good to, it's a quicker way to kind of get the overview here, and then you can also go back and read the words as well. So I can go ahead and read figure 4. Yeah, figure 4, similar to figure 3, but with the swarm bee trajectory in the northern hemisphere mapped to 425 kilometers in the southern hemisphere on the left. Sorry. On the left is the unwarped all-sky image from Dunedin. The symbols do not overlap exactly with the thin white-greenish arc, which is evidence of a lower emission height. On the right, the electron density decreases down to 10 to the 4 per centimeter squared, and the electron temperature reaches 10,000 degrees Kelvin. The horizontal velocity increases to 10 kilometers per second, and the plasma channel width is thinner. So there's a lot going on here. We may have to actually delve into the text here, but what I'm going to say is this is the next conjunction time they could get. So this is the same satellite, but compared to figure 3, which the time was at 9:40, satellites move really fast, and what they're using here is this satellite crossing half the Earth and being up in the northern hemisphere at approximately the conjunction point of that maps down to this kind of equivalent point in the southern hemisphere as well. So that's how they're getting a second conjunction time 20 minutes later. And you can also see that it's moving west in terms of where it's crossing this arc. And then you can also see that at 10 o'clock from Ian's warped image or unwarped image, that's much more into the sort of picket fence time of this Steve. And so what does the satellite that's measuring the ionospheric conditions at the same time reveal in comparison? And so that's where we want to look at the right-hand side of figure 4 compared to figure 3. And I'm about to flip back and forth. One thing I'm going to look at is, did they put those figures on the same axes on the y-axis? And they did not. So like, for instance, if you look at the velocity, which is the lowest, the third panel, the lower panel, you can see that the scale on the first one in figure 3 only goes down to 6,000, minus 6,000, whereas that peak in figure 4 goes all the way down to minus 10,000. So what that means is 20 minutes later, when this swarm satellite is collecting data in the northern hemisphere, that's approximately in the right across this arc, it is, or across this structure that now is looking much more Steve-like, the velocity of that structure that you're cutting across really quickly is now 10,000 meters per second. And if you move up to the second panel, the electron temperature, you can also see that that peak in electron temperature has gone up to, it's even more than 10,000 Kelvin, whereas in figure 3, in figure 3 it was more than 10,000 Kelvin as well. It was like 1.2 times 10 to the 4, and here it's maybe 1.3 or 1.4. Anyway, it's a little hard to tell because they're not quite on the same scale, but and then you can also look at the shape of that density channel. And in that case, what we want to see is it, those density channels are like where the Steve is in the ionosphere. It's in this kind of channel of much lower density. And so what we sort of care about is that density channel broader or deeper? And so compared to figure 3, it's kind of, let's see, I can try and read the value of the density, that how deep it goes down. Maybe it's 4 times 10 to the 4. And it's definitely deeper and broader in figure 4. So it kind of evolves into this, in the ionosphere, this region that is a stronger flow, a deeper density channel, and a little bit higher electron temperature. Are you guys can I explain any of that? Do you have any questions about that or other questions about the figures?
Only one general question. This is a measurement from the northern hemisphere, and Steve was in the southern hemisphere. What is known about the similarity of the ion drift speeds at the same time in both hemispheres? Are there measurements showing that both velocities are more or less the same, or is this just an assumption that both velocities are the same?
That's a super good question. In order to have those simultaneous measurements of some channel, like the Steve channel, also known as a subauroral ion drift channel, you would have to have satellites in both, cutting across those at the same time. And I don't think that satellite-wise we have that opportunity very often. However, there are a lot of, the Steve lasts for like an hour, or a really long-lasting Steve. You could look on that swarm track for, here it's on the north, here it's on the south, and they are pretty equivalent. So I think the assumption is that they're similar strengths of channels in the north and the south. And in this case in particular, they are making that assumption because they're showing the northern hemisphere satellite pass, and they're equivalent, making it in comparison to the image in the south, and they're drawing conclusions from that. So they're they are making that assumption. But I think it's a good assumption.
Yeah.
The thing that is more can be more difficult or tricky with the northern southern hemisphere assumptions are the mapping, the exact mapping of that crossing and where it's crossing the other hemisphere.
It would be great to see satellite data for Steves that last long from swarm, for example, for different orbits, showing how the drift speed changes during the orbits.
Yeah, that's a really interesting point. And I think there are some papers. There must be some papers that do that, but I'm not quite sure off the top of my head which ones look at that. Look at successive passes and study the widths of these channels. There's definitely a paper, like a big paper on SAID statistics that
I know it.
But then that's not the same event, so you don't get the sort of evolution of
Okay.
And that's something that Michael, as you're suggesting, could possibly be done with more observations, right? So if you have a night where you have both hemispheres with the observations and the conjunction, it's you can get more looks at that.
Okay, thank you.
What else? Okay, so this is pretty cool that you can see in this case how Ian's images at these two times, he had a whole time lapse, and it's because he had the time lapse that you're able to pick out what ends up being like 2 frames in this paper, which are the frames where his image captures the look of the event at exactly the time that a satellite was crossing it, more or less.
Just wanted to give us a time check. We have about 5 minutes left.
Oh, okay, great.
Wrap up.
How many more figures do we have? I think we should go ahead and we have one more figure, but just try and read the conclusion to give it sort of a sense of that. Actually, there's definitely more details, and if you're kind of intrigued, you can check out the, I was going to say discussion section, but basically this paper is short, so it's all discussion here. Yeah, let's read the conclusions, because I think we've basically built up into this, and really good set here. Francesca, would you mind reading the conclusions, possibly?
Yes, I can.
Thank you.
On 17 March 2015, citizen scientist images from Dunedin, New Zealand, show the evolution of a bright SAR arc into SIV. The SAR arc was also measured by an all-sky imager at the Mount John Observatory, around 200 kilometers north of Dunedin. The SAR arc was unusually bright, reaching around 6 kiloray. The SAR arc changed its width and emission characteristics by 9:45 UT and became a thin white purplish structure, resembling a typical STIV, with a green picket fence structures also observed, moving rapidly along the arc. The height of the initial arc was determined to be 425 kilometers, but later a lower height seems more appropriate. Complementary information from Swarm B satellite data shows that the bright SAR arc was accompanied by large changes in the electron temperature and westward plasma flow. The plasma perturbations observed at the magnetic conjugate location of the optical observations were more extreme, with apparent values of velocity, horizontal velocity, reaching as high as 10 kilometers per second, and electron temperature about 10,000 Kelvin. Evidence from DMSP satellite data also points to an extended subaurora structures with plasma parameters changing between 9:15 and 9:45 UT. This work reports the first observation of a transition from SAR arc into STIV. This evolution is accompanied by a transition from unshade into an extreme shade in less than 30 minutes, with horizontal velocity and electron temperature values exceeding previous measurements at subauroral latitudes. This result highlights the fast dynamics of the subauroral region and present a challenge to theories and models of subaurora structures, their generation mechanism, and how they relate to each other. This study shows the benefit of combining citizen scientist observations with scientific data to help discover new connections in geospace.
Yeah. This is a very nice study. The one other thing I was thinking about from this study is noting the date. This is the St. Patrick's Day storm of 2015, which was a very large storm. So things are unusual, like that makes it unusual. And then this is only kind of one observation. It's definitely worth bringing up, like the recent smaller storm where something perhaps similar to this was seen. So, Francesca, did you want to say anything else about the conclusion or ask anything?
No, I think it's important to highlight the brightness that reaches 6 kilorays, and yes, the development between the SAR arc into STIV, in order to understand if we have the same mechanism that start and develop itself, or two different mechanisms that happen together at the same time. This is my main question.
So more work remains to be done, Laura, before we can decide if it's a baby Steve or how the, you know, what happens between them. But it is very interesting. So Thank you all. Thanks to Vincent for joining us. You are late, but you're welcome. We've had a good discussion of the paper. I assume you're joining us from Churchill, Manitoba to show us the polar bears outside your window or something like that. But yeah.
I got the time zone wrong. Plus, I was asleep an hour ago anyway, so.
That's
Catch
fair.
up on your sleep. Yeah, that's good. Great. Well, hopefully this helps go through this paper a little bit. We are going to be able to talk to Carlos and maybe Bea and maybe even Ian in our ambassador meeting in a couple weeks. And I think we definitely should pull up the movie of this event. And definitely, I think you also kind of now have more of a framework to delve into some of the questions and the more technical text. So everyone's invited to do that. You know, you can see the references to past work and all kinds of other pieces of it too. So
well, I must add, like this paper actually says quite a few things that I noticed that day, so it's super helpful. I think it sort of, that's what was going on at the end of August.
That's so cool.
Yeah.
You should definitely bring those observations to the meeting as well.
Sure. Yeah.
If you want to put a couple slides together, that might be good because now you've kind of seen how it was done like in this paper. So if you had some examples or a movie with timestamps or something like that, that might be nice to, to appreciated by everyone. Yeah, thank you.
So can we not do the measurement like it was done here using satellites all the time? Like the satellites happen to be there, right? That does not have. Like, was there any measurement done that day, or do we know about it?
I don't know, and there are some ways to check in the data availability of this paper. It talks about where the swarm data are available. And then it also talks about, there's also another platform called Aurora X, which is a University of Calgary platform that does make looking for these conjunctions more easy to do. So especially if you have the times, we can try and see if that's available too. Yeah, very interesting. Thank you. All right, we'll sign off for now.
Well, thank you guys so much for being here. We really appreciate it. And we'll hope to see everybody at the ambassador meeting. I will send everyone who's here an invitation. And yes, Vincent, absolutely. Good luck, everybody. If you're going chasing, we are applauding and cheering from sad Northern Lights-less, Southern Lights-less latitudes. So living vicariously through you all.
Thanks.
All right.
Thank you.
Thanks, everyone.
Bye-bye.
Bye.
Bye.
Bye-bye.
Thank you. Bye.